Ladies and gentlemen, at this time, please turn your attention to the screens for a short message from our sponsor, 2 Sigma.
We use data to try to predict things. In particular, we want to predict the movement of the markets that we invest in. In a lot of ways, data is sort of core to everything that we do. We look for data everywhere we can. When we go home at night and read newspapers, we might see a data set referenced there. The first thing that will come to mind is, hey, do we have a copy of that? How can we learn more about that particular data set? For every data set that we want to look at, there's going to be someone that has the technology to help us get that data. So we'll have to reach out and work with our engineers who can sort of help discover where that data set is, make sure that it's clean and available, and download it in a way that we can, as modelers, explore. We have a lot of data. It's very exciting. You can come in every day, and a lot of the time you say to yourself, I wonder if I could study this. And you look around and you realize that we've been collecting it for 5 years. And so suddenly you have this very rich playground of information to go and explore. I came here because the people, I really like the people I met when I was interviewing, and each day I'm coming in surrounded by some of the top people in their respective fields. I like that it's an exploration. You never know what you're going to find, right? You have this idea, it's a hypothesis, and you say to yourself, maybe if this is true, then I'll be able to find it in the data. And so you go in, and you don't know the answer until you really dive and slice and dice. And when you find that sort of signal, that thing that can predict the future of markets using public data, it's a really exciting feeling, and it's probably one of the best for a modeler when you find something, right? It's really cool.
I think I describe the people at 2 Sigma as passionate. They are incredibly smart, incredibly giving, and easy to work with. They're passionate about things you'd expect like mathematics and science and engineering, but they're also passionate about helping people. They also have a lot of interests outside of work that they bring to bear on the problems that they have to solve at work. Suzume really encourages people to bring their outside passions into work. So one of the things that I do is I organize a book club. We call it Read On. We started out with popular science books like Predictably Irrational by Dan Ariely. It talks about how people have cognitive biases. We got together, we read this book, and we can apply some of the ideas to how we think about investing, how we think about strategies, for example. I think it's really important for me to work at a place where there are people that I want to be like, where there are people that I want to learn from. It's really nice to gather with coworkers and share these interests. It makes me feel like it's really a place of learning.
Ladies and gentlemen, please welcome to the stage Vipin Kumar.
It's my pleasure to introduce the keynote speaker today, Cynthia Rudin, who's a professor of computer science, electrical and computer engineering, and statistical sciences at Duke University, where she directs the prediction analysis lab. And her focus of research is on interpretable model, not just accurate model, but interpretable model as well. Prior to joining Duke, she was a professor of statistics at Sloan School of Management at MIT. She was chair of data mining sections at the American Statistical Association and at the Informed Society, which is one of the largest societies of the operational research. She has a long list of honors and awards. So she's a 3-time winner of the Innovative Applications Award from the Informed Society. She was named among the best professors in business school that are 40 under 40 worldwide just a few years ago. She was also voted as among the best professor at MIT just a few years ago. She's a fellow of the American Statistical Association, fellow of the Institute of Mathematical Sciences. She received her bachelor's degree from University of Buffalo, also known as SUNY Buffalo to many of us, and PhD from Princeton University. Please join me in welcoming Cynthia for the keynote. Okay.
All right. So I work in interpretable machine learning, and over the years, I've seen the field of machine learning lean more and more toward complicated models, even when we don't need them, and when simpler models would suffice. And I didn't want to just give a talk that says, stop using black box models, because that's not constructive. That's destructive. I wanted to tell you not just don't use black box models, but I wanted to tell you why you don't need them. So I'll give you an example of recidivism prediction in the criminal justice system. Right? They use predictive models to determine people's risk of being arrested in order to determine whether to release someone on bail or parole. And in some cases, these models are so complicated that it's easy to compute the predictions incorrectly. So this New York Times article is about a case where a typographical error in the input to a predictive model led to someone being left in prison for years. Right? The typo was in his criminal history features. And the model that the justice system was using for his prediction was called COMPAS. And you'd think these black box models like COMPAS would be really accurate, given that they potentially use over 100 features and that, they come from this company. But these models are actually not that accurate. So we did an experiment with some very famous data from Florida to test the accuracy of this particular black box model, which is called COMPAS, again. And COMPAS is used very widely throughout the justice system, the US justice system. Okay, so in this experiment, we compared the accuracy of scores from the black box with the scores created by our latest machine learning method at the time, which is called corals. Now, corals is just certifiably optimal rule lists, and it produces decision trees, one-sided decision trees, or decision lists, that are certifiably optimal and sparse. Okay, so I'm just going to show you the model that corals gave us. So the model is so small that it can actually fit on the bottom of a PowerPoint slide. And here's the model. So the model says if you're young and basically if you have young and lots of prior offenses, you'll probably be arrested in the future. So if you're 19 to 20 years old and you're male, predict that you'll be arrested within 2 years of your COMPAS score calculation. Also, if you're 21 to 22 years old and you have 2 to 3 prior offenses, predict arrest within 2 years. Also, if you have at least 3 priors, predict arrest, or greater than 3 priors, predict arrest. Otherwise, predict no arrest. Okay, so this is the optimal sparse decision list for this data set for predicting arrest. And the question is, how accurate are these two models, right? And as it turns out, they're just about the same accuracy. And we did 10-fold cross-validation. Corals produces essentially the same model in all 10 folds. And the different colors are just the different folds. And so you see that these two COMPAS and Corals are about equally accurate. But what's even more interesting is that it doesn't really matter which machine learning method you use. They all kind of perform the same. And, you know, some of these are complete black boxes like COMPAS, which is proprietary. Or, you know, you could have support vector machines with radial basis function kernels or boosted decision trees with hundreds of trees. Like, they can be very complicated, some of these models. And on the other extreme is Corals, whose whole model is right there. Now, there was a huge debate about the algorithmic fairness of COMPAS. But the truth is that we just don't seem to need COMPAS at all. So why are we still using it? Now, back to my point here. Perhaps we are using complicated models when we don't need them. And there does not seem to be any benefit from complicated models, at least for rearrest prediction in criminal justice. And there's been a lot of work on this even before the ProPublica article came out, even before all this fairness literature. So, as it seems to be, though, there doesn't seem to be any benefit from complicated models for lots of other problems. And I've listed a whole bunch of problems in energy reliability, finance, and healthcare. These are all problems that I've worked on where we didn't seem to need a very, very complicated model. Now, I think, though, that the answer to this question depends on your data representation. Because, you know, neural networks are really great when you need a good data representation, when you need to create one. Like for computer vision, right? You need to create a good representation. But if your data naturally come with a good representation, then all the algorithms tend to perform the same. So why, then, are we still using complicated models for problems when we don't need them? Well, there's a lot of really good reasons. First of all, people really like them. And they're also, you know, they're profitable, and they're much easier to construct than simpler models. Okay, so, you know, if the models were too simple, you can't keep it as a proprietary secret. Right? All three of these models, by the way, have a record of causing some serious harm to people by being proprietary. Right? Brizometer, they told people that it was safe to go outside during the California wildfires when people were reporting a layer of ash on their cars on the same days. And incorrect FICO scores, of course, can make it difficult for people to get a home loan. Anyway, these guys have a real incentive to keep their models complicated. But most of my talk focuses on this problem, which is that complicated models are much easier to construct than simpler models. It's kind of ironic that complicated models are easier to find and that simple models can be very, very hard to find. So let's say that we are doing supervised learning, just regular supervised learning where we want to minimize a loss function to make our models accurate. But now if you also want it to be simple, you have to constrain the optimization problem to force the complexity of the model to be small. And once you get to the constrained optimization, and depending on the constraints, this problem becomes much harder. Okay, so if the problem on the left is about finding an accurate decision tree, that is much easier than finding an optimally sparse decision tree with the same accuracy. It's exponentially harder. And if the problem on the left is to find an accurate linear model, well, we can do that with regression or logistic regression, but then once you add sparsity constraints, the problem becomes much harder. Okay, so what about if you just unleash the most complexity you have on the problem, and you go with your favorite neural network or boosted decision tree, and they're very accurate? And then my question, though, is, well, can you get the same accuracy if you use an accurate and sparse decision tree? Or maybe if you use even just a little tiny linear model? Or what about if you're doing computer vision and, maybe you could create a neural network that is constrained somehow to be interpretable? Now, when I'm doing these things in practice, I want to know, am I going to get the same accuracy by solving the constrained problem as I am with the unconstrained problem? Right? I want to know if I need to sacrifice accuracy in order to gain interpretability. Is it worthwhile for me to bother solving the right-hand problem, or am I going to lose so much accuracy that it's not worth it? Right? The right-hand problem is much harder than the left-hand problem. Okay, so here's one of the questions I've been thinking about for a while. Can I determine whether this equality approximately holds in practice without solving the more difficult optimization problem? Right? The optimization on the left is easier than the one on the right. Is it going to be worthwhile for me to bother solving the one on the right? So in other words, can I determine the existence of an accurate simple model before I actually go to the trouble of finding one? Okay, so the first part of this talk is sort of a perspective on learning and simplicity. And I'm going to try to define a condition under which a simple yet accurate model is likely to exist. And the second part of the talk is an overview of some of the projects going on in my lab, where I'll talk about computationally efficient solutions to some of these hard optimization problems that lead to interpretable machine learning models. Okay, so the condition is that something called the true Rashomon set is large. All right, so the true Rashomon set is the set of models with low true loss. So I want you to think about abstract function space along the horizontal axis, and then the vertical axis is the expected loss over the whole distribution of data that you're drawing from. So the Rashomon set is the set of models with low true loss. Okay, so it's the set of functions such that the expected loss is below some theta that you determine. Okay, so I claim that a possible explanation for what I'm seeing in data is that if the true Rashomon set is large, a simple yet accurate model is likely to exist. Okay, so this is kind of like a big ocean theory. The bigger the ocean, the higher the chances are that you'll find a big fish. Right? And the larger the Rashomon set is, the larger the chance that you could find a simple function in there somewhere. Right? There's so many good models that hopefully at least one of them is simple. Okay, so I'm just going to change my notation just a little bit, where the expected loss is just going to be called L. Oh, by the way, I know I've drawn a very nice, smooth function there for the expected loss, but it doesn't have to be that way. Actually, I could have drawn something that was totally, non-convex, and the Rashomon set would be disjoint, right? And that's okay. So I want to show you the simplest possible abstract setting that I could think of to show you how this thing at the bottom could happen. Okay, so I'm going to have two finite hypothesis spaces, the set of simple models and the set of all models. And the simple models are contained in all models. And here I'm going to have the simple models drawn uniformly from all models without replacement. Now, I know this is abstract, and I know that simple models aren't randomly drawn from a more complex model class. But in reality, as long as each complex model is reasonably close to a simple model, the same idea is going to work. Okay, and then my loss function is bounded by B. And then F2 star is defined as the best possible model if you know everything. If you have the entire function class at your disposal, and you have the whole test, all the test data, you have the whole distribution that the data are drawn from, F2 star is the best that you can do. F1 hat, on the other hand, that's a model you can construct from your data. Because here, and you're only allowed to use simple functions, okay? All right. So, for F1 hat, you have only access to the training set, and you're restricting yourself to work with simple models. And the question then is going to be how good F2 star can do on the test set compared to how good F1 hat can do on the training set. Okay, so I'm just going to simplify notation a little bit. So again, L is expected loss, L hat is average loss on the training set. And I want to know, I want the best true risk of the complex class. So in other words, I want L of F2 star to be close to the best empirical risk of the simpler class. So I want L hat, F1 hat. So I want these two things to be close together. Now, I don't want to do regular learning theory, right? I already have standard learning theory. Learning theory tells me how close, L hat of one function is to L of that same function. I already have that. What I want is to know how good I can do if I knew everything versus if I'm restricted to simple models on my data. Okay, and I'm going to use the Rashomon set to help me with this. Okay, in particular, I'll use the Rashomon ratio. So the Rashomon ratio is just the fraction of models that are good. It's just, the fraction of models that have low loss. Right, it's just the number of models that have low loss compared to the number of total models. Okay, so it's the fraction of good models. All right, so that's the Rashomon ratio is going to help me out with this. Okay, so here's the theorem. So it says, for any epsilon that you pick, with probability at least 1 minus epsilon times p, and I haven't told you what p is yet, with respect to the random draw of the functions to form the simple class, and with respect to the random draw of IID data, I have this inequality holding. So in other words, these two quantities that I want to be close are actually close and is bounded by something that has to do with the simple function class, not the more complex function class, the simpler function class. And better yet, the probability with which this bound holds depends on the size of the Rashomon ratio. So you get kind of the best of both worlds from this bound, right? The best simple model on the training set isn't any worse than the best complex model on the test set, and the bound is nice and tight. It depends on the size of the simple function class. And it also depends on the Rashomon ratio. So the bound is likely to hold more often when the Rashomon ratio is large. Now, I know the probability here is a little bit inscrutable, but I could give some examples. So for instance, if I'm working with 100,000 functions, and the Rashomon ratio is at least 1%, so at least 1% of models are good, then the bound holds with 99% probability when you have at least 526 simple models somewhere in there. And then if I lower the Rashomon ratio, you can kind of see what happens. So again, if I'm working with 100,000 functions, and the Rashomon ratio is at least 0.5%, so 0.5% of the models are good, then the bound holds with 99% probability when you have just over 1,000 functions in the simple class. Okay, so in other words, the bound says that if the Rashomon ratio is sufficiently large, then with high probability, the best empirical risk over the simpler class, F1, is close to the best possible true risk over the larger class F2. And this generalization guarantee comes from F1. Okay, so I just want to mention that the Rashomon ratio is not the same as any other classical measure you'd find in statistical learning theory. Right? Large Rashomon ratios pertain to the existence of models with good generalization. They are not functioning in the same way as in standard learning theory. And they are not the same as standard learning theoretic measures. So I showed you one of several generalization bounds that includes the Rashomon ratio. I'll show you another one in a minute. But the Rashomon ratio is not the same as the geometric margin that's used in support vector machines. The margin is measured with respect to one model. The Rashomon ratio is measured with respect to all models. It's not the VC dimension. The VC dimension is data independent. To calculate VC dimension, you move the data around to try to shatter points. Here, the data set is fixed. The Rashomon ratio is a property of a loss function on a data set. This is not algorithmic stability. Stability is a property of an algorithm in the way an algorithm searches a space. Here, it's just a property of a loss function on a data set for Rashomon ratio. This is not the same as Rademacher complexity, which measures the ability to fit noisy targets. The Rashomon ratio uses a fixed data set. And it's not the same as a flat minimum, because the Rashomon set, as I showed you earlier, could consider many local minima. You could have many local minima that could be a Rashomon set. You don't need one flat minimum. Okay, so the next theorem also guarantees the existence of a simpler model that is in the Rashomon set and generalizes well. Here, I'm going to work in infinite function spaces, so no more uniform sampling, and now we're going to assume approximating sets. Okay? So I need some more conditions on this theorem than for the last one. So the conditions are basically smoothness. So smoothness and good approximating set. So I need a Lipschitz loss function, and that the simpler class F1 is a good approximating set for F2. And also the Rashomon set, of course, is going to be large. And the proof of this theorem is essentially one line long. So I'm hoping by presenting you something that seems to be obvious that I will be able to kind of get my point across more easily. Okay, so I'm going to put the theorem up, but I'll explain it intuitively first. So F2 is the set of all models, and F1 is the set of simpler models. Okay? And then the Rashomon set is big. It's the set of good models. And then the theorem is going to tell us, when I read it, the theorem is going to tell us that the Rashomon set has to contain a ball. And the ball has to be big enough so that it contains at least one function, like that guy right there maybe, that guy right there, that is a simple function that generalizes well. Okay, so let's read the theorem. So the theorem says for a smooth loss, K Lipschitz loss bounded by B, hypothesis spaces F1 and F2, where F1 is contained in F2, if for each F2 in the Rashomon set, there exists a model F1 in the simpler set that's close to it, and if the Rashomon set is large enough in that it contains an LP ball of size at least delta, then there exists a function, F1 bar, in that Rashomon set such that for any epsilon you give me, F1 bar is from the simpler class and it generalizes well. And in particular, the generalization guarantee depends on the complexity of the simpler model class of F1. This is the Rademacher complexity of F1. Okay, so if the Rashomon set's large enough to contain a ball, then it contains a simple function that generalizes well. All right, so these results suggest that if F1 is a good approximating set for F2, and the Rashomon set is large, then we might as well just be working with the simpler class. Right? So for example, if decision trees approximate support vector machines with radial basis function kernels, and for my particular problem, the Rashomon set is large, then I can just work with decision trees. I don't need the SVM, right? I can just work with decision trees. because I'm not going to lose any accuracy. All right, so also I should mention that the result on the previous slide can be generalized under similar conditions to say that all functions in F2 generalize based on their proximity to functions in F1. And again, this would still use the complexity of only the simpler model class F1. All right, so that's what the theory says. Let's find out what happens in practice. So we wanted to know what Rashomon ratios look like in reality, but of course you would never actually want to measure them in reality, because measuring them is a disaster mess, right? You would have to look at every single function in your function class to do it. So we're going to do it anyway, just to find out what happens. And in particular, we're going to calculate the empirical Rashomon ratio, which is the fraction of models that are good in training. And again, we're just going to do this today to see what happens. And what we found was pretty interesting. And as we found out, you don't actually have to calculate the Rashomon ratio in reality to gain practical insights from it. Okay, so we're going to do an experiment where we calculate the size of the empirical Rashomon set using decision trees of depth 7. So why did we choose decision trees of depth 7? Well, first of all, decision trees can be sampled. So that allows us to sample from our set of functions. And also decision trees of depth, depth 7 is pretty deep. It's deep enough for, we weren't working with very, very complicated data sets. So the decision trees of depth 7 were a good approximating set for our particular data sets because they were able to fit them without overfitting too badly. Okay, so I want you to think about a function space that contains models from lots of function classes, like not just trees, but SVM, boosting, random forest. Just think about, like kind of a bigger function space that includes functions from all those classes. I want it to be big enough that it includes those functions, but I don't want it to be too big or it'll overfit. So I just want it to be big enough. And I want you to think about us approximately covering that set with decision trees of depth 7. Okay, so separately, we're going to look at the performance of many popular machine learning methods on the same data set. And we want to figure out if those methods all perform similarly. Because you see, if the Rashomon set is big, it means the Rashomon set can accommodate a lot of diverse functions. So if you have all of these different methods performing the same, that means they're all in the same Rashomon set. And that means that Rashomon set can contain very diverse functions. Right? SVM are smooth. Forest is not so smooth. Right? So if the methods perform similarly when there's a large Rashomon set, our theory is right on track. Now, also, we evaluated whether the methods generalize, because our theory tells us, that I just showed you, the theorems tell us that the methods should generalize well when the Rashomon set is large. Now, I'm going to show you the experimental results in a second, but I'll give you the punchline now, which is that when the Rashomon ratio was measured to be large by the decision trees, all the methods tended to perform similarly and generalized well. Interestingly, the reverse was not always true. And I'll tell you about that in a minute. Okay, so we experimented with 36 data sets, all from the UCI machine learning repository, because they're all public, 15 categorical data sets, 21 real value data sets, features ranging between 3 to 784, and the number of classes ranging between 2 and 6. Okay, so when we had a large Rashomon ratio, what we would find, so this is just 4 data sets, many different machine learning methods, and training and test performance for each method. So this is what we found every time there was a large Rashomon ratio, is that all the methods perform the same and they generalize well. When there was a small Rashomon ratio, sometimes you'd get stuff like this, where the methods performed completely different from each other and then they didn't generalize. But sometimes you would get something like this, where everything just generalized perfectly. And we think that this has to do with the way we're measuring the Rashomon set. We think that the Rashomon set can appear artificially small if there are some extra features in the data set that don't do anything. Okay, so the results of the experiment say that if the Rashomon ratio is large, all the methods tend to perform similarly and generalize well. And we didn't see any exceptions to this. But if you can't measure the Rashomon ratio in practice, that's okay, because the experiment says that if all the methods tend to perform similarly, they tend to generalize well. And this could be, doesn't have to be, but it could be due to a large Rashomon ratio. If all the methods perform differently, it's likely a small Rashomon ratio. Now, we're not completely sure about this yet, but certainly I think this is a viable, possible explanation for what's going on. Now, we found something else besides the results I just showed you. And what we plotted is something called the Rashomon curve. Now, we weren't expecting to see this, but we found it on every single data set that we worked with. And I'll show you a cartoon of it. It's a plot of the Rashomon ratio versus the empirical risk. Okay, so let's say you take a hierarchy of function spaces from the least complicated to the most complicated. So I want you to think of F1 as being like decision trees of depth 1, and then F2 is decision trees of depth 2, and so on and so forth. So you have this hierarchy of hypothesis spaces. They're all contained within each other, getting more and more complex. And as you increase complexity, what happens to the empirical risk? Right? It goes down. Because as you have more and more complicated function classes, you can fit the data better. So the empirical risk goes down. So then, okay, what happens to the log of the Rashomon ratio? Well, that one's not so clear, because you see, as the classes of functions become more complicated, the Rashomon set gets larger, but the denominator of the Rashomon ratio gets larger much, much, much faster. So in fact, the Rashomon ratio tends to go down. Okay, so again, the Rashomon ratio is just the fraction of models that have low empirical risk, okay? So it's the fraction of models that are good. All right. So what happens when you do this is that as you start with very, very simple function classes, the empirical risk goes down very quickly. Like as you increase from depth 1 decision trees to depth 2 decision trees to depth 3 decision trees, the empirical risk goes down. You can fit the data better. But interestingly, the Rashomon ratio doesn't really change that much. And then what happens is it takes this nosedive. Like all of a sudden, your empirical risk doesn't change very much, but the Rashomon ratio just it just gets really, really small very, very quickly. Okay, and sometimes you see a little bit of overfitting, but the overfitting is like tiny compared to like how quickly this thing goes down. Like it nosedives so fast that you don't even see it. And there's some variation in the shape of these Rashomon curves. Like sometimes you see like it's flat, or like sometimes it'll go kind of up and then down, because for these kinds of spaces, the Rashomon set is so small that the ratio can be kind of a little bit funny and be very small. But there's always some kind of elbow, right? There's always some kind of turning point. And you'd never see this curve with other complexity measures, because they're not data dependent, right? If you tried to plot VC dimension on the vertical axis, you would never see it flatten out, because VC dimension always increases as you increase the complexity. You'd never see it flatten, and you certainly wouldn't see it go down a little bit, right? So this is really not obvious. Okay, and sometimes you only see part of the curve. You might see the horizontal part, or you might see the vertical part, depending on sort of just depending on your data set. So we did some experiments to investigate this Rashomon curve. And again, we were using sampling of decision trees. Now, for each point on the plots that I'm going to show you, we sampled over 2 million decision trees of that depth. So this was a kind of expensive experiment. And again, we used our 36 data sets. We chose the Rashomon parameter to be 5%, but we changed the Rashomon parameter around, and we got the same thing. Okay, and the Rashomon curve held for every single data set that we investigated. So this is just the illustrations up on the top, and here's some samples of the data sets on the bottom, where you can see the nice curve here. Here it flattens on the top. Here it kind of does this funky thing like there, and here you only observe the vertical part. Okay, so I can't fit all 36 data sets on one slide, but I can fit them on 2 slides. So there's the real valued data, and you can see these curves on every single one of these data sets. So here are these very pretty Rashomon curves that look just right, and here just the vertical part. Here's the little kind of strange hook. And here are the categorical data sets, and again, you're seeing the same sort of thing. So you might say, okay, fine. That was the training set. What about the test set? So for the test set, learning theory tells us what should happen. Standard learning theory tells us exactly what should happen. Because for simpler model classes, we should generalize better. So, and as we get to more complex model classes, we should be overfitting more. We just shouldn't generalize as well. Okay, so the best test error would be here, right around the elbow in this illustration, right? So if this is training, that's test. The best test error is kind of here, right? So test error goes like this. So here we chose a different class of a different set of hypothesis spaces just for changing things up. Here we work with linear models rather than decision trees. We're working with the hierarchies being created by adding more and more polynomial features. And we're doing regression instead of classification with the squared loss instead of the classification error. And here the Rashomon ratio is computed analytically. So there's no more sampling 2 million decision trees. It's all computed analytically because as it turns out, the Rashomon set is an ellipsoid, so you can actually compute its volume in the high-dimensional space. And we found basically what we expected. Sometimes theory is very insightful, and it tells us exactly what should happen, and it all works out beautifully. The minimum test error is sort of here, and it's all nice and perfect, right at the elbow. But sometimes we always generalize. If you have a lot of data, you always generalize. And sometimes you never generalize, and that's just standard for learning theory. But in any case, the elbow model, the model right at this elbow, always seemed to be kind of a good choice for model selection. I mean, even when learning doesn't really work, the elbow didn't seem to be a worse choice than anything else, right? Even in cases where it just didn't work, you weren't hurting anything by using the elbow. So the elbow is kind of a good level of complexity to aim at for model selection. So then, in real problems, though, you don't always end up having the whole curve, right? You land on part of the curve when you're doing your experiments, but you don't always know which part. So we might want to figure out where we are in the Rashomon curve in order to determine whether we're above or below the elbow. And remember, you can't measure any point on this curve. You just have no ability to even measure a single point. So if you're in this part, then if you run a whole bunch of different machine learning methods with different levels of complexity, the best model for each of those different complexity levels is going to have different performance. So for machine learning, you have different algorithms that produce models of different complexity. So if each of the different machine learning methods performs differently, you're probably on that part of the curve, the part on top. And then if you're on the vertical part of the curve, then no matter which machine learning method you use, with its own level of complexity, it's going to perform approximately the same as all the other ones. Okay, so in that case, maybe here your models are overly complex, so you could potentially reduce complexity to find models that are simpler or that generalize better. So I've been thinking that this might explain some of the things that me and others have been observing across problems and across data. Right, there are some problems like ImageNet where the field has been designing more and more complex models, and where that continues to reduce error. So maybe we're on this part of the curve still for ImageNet, and then adding more complexity would help. And then on the other hand, if you consider problems like MNIST, where no matter which method you use, you get 100% accuracy. In that case, maybe we should be aiming for simpler models that might have other properties, like interpretability, or they might generalize better outside of MNIST. And then there's a ton of problems of the kind that I usually end up working on. So I pick my problems based on the application rather than based on sort of my machine learning method. So I always end up working on these kind of problems where, like rearrest or stroke prediction or something like that, where it doesn't really matter which machine learning method you pick. They all tend to perform the same. Just like for the rearrest data from Florida that I showed you. They all tend to perform the same. And also for these problems, you can't get a particularly accurate model no matter what you do. So the empirical risk is fairly high. So you get kind of low accuracy because there's an underlying level of noise in these data sets that there's nothing you can do. I mean, if you use a more complex model, you just overfit. And so for these types of problems, we want to lower complexity to walk up toward the elbow. Okay, so what I've gotten to is a simple check that doesn't involve computing Rashomon ratios that can give you some general advice. Pick several of your favorite machine learning methods. Run them all on the data. If they all perform differently, your model class could be too small to include the Rashomon elbow, in which case you might want to broaden your horizon and use a more complex model class. Now, if all the methods perform similarly, well, in that case, your model class might be more complicated than necessary, or might be larger than necessary, in which case you could try to delve in and find specialized models with specific properties like interpretability or other types of constraints that you might want on your model, like ease of computation in practice or anything like that. Or you could try to look up. You could try to improve generalization without reducing accuracy by choosing a simpler model class that would move you upward on the, toward the elbow without decreasing accuracy, but just decreasing complexity. Now, I like this analysis because you essentially benefit from knowing the size of the Rashomon set without ever having to calculate it. And like I said, this is just a theory, but I think it's a reasonable explanation for what could be going on in problems like rearrest. Okay, so back to the talk outline. So I've defined my condition, which is that the true Rashomon set is large. And as I said, you don't need to calculate the Rashomon ratio. You can try lots of different machine learning methods, and that gives you a sense of whether simpler solutions are likely to exist. Now, a ton of people don't actually believe me about this, or they aren't interested, and that's fine, but sometimes it gets a little silly. Now, before I talk about what we're doing in the lab, I want to tell you a story that happened earlier this year. So last summer, about a year ago, we found out about the FICO Explainable Machine Learning Challenge, and our group decided that we had to enter it. Now, the goal of the competition was to create a black box model for the FICO data and explain it. And we got the data set, and I took one look at it, nice big data set, but it looked, just at a glance, like it had a good data representation. And I thought, could I be wrong? Could it be a problem with a good data representation where you actually need a black box and then explain it afterward? So I said to my students, well, I don't know about this competition. I said, just try running a bunch of algorithms on the data set and see whether they all perform the same. So a day or so later, my students emailed me back, and they said, indeed, all the methods perform the same. And so we pretty much knew at that point that we could construct an interpretable model for this data. And at that point, we had a debate. Should we send it an interpretable model with the same level of accuracy as the black box, which the judges probably wouldn't know how to deal with because it's, we're not following the rules of the competition, or should we actually follow the competition and create a black box and explain it afterward? So we decided in the end, after a very short debate, that for a problem as important as credit risk, we should create an interpretable model. So we did. We created a globally interpretable model with a beautiful visualization tool with the same accuracy as the best neural network that my students could construct. And my students are very good at constructing neural networks. So, and I'm just going to show you some snapshots of the visualization tool. It was very pretty. There was lots of stuff you could adjust. The colors were meaningful. They told you which features contributed to the model. And you could press buttons to get pieces of the model to come up. It was actually 10 subscales, like 10, the features were grouped into 10 subscales where there was a sparse logistic regression model for each of them. And then at the end, these 10 subscales were combined into a final logistic regression model. So we called it a 2-layer additive model because it was an additive logistic regression model. Okay, so if you push one of the buttons for the subscales, you get all the details of exactly what the calculation was. So here I'm showing you the delinquency subscale where it looks at the percent of trades never delinquent, and you get points for what percent of trades were never delinquent, and then the month since the most recent delinquency, and so on. You get points for all those things, and the points, these 4 things add up and give you the total number of points for the delinquency subscale. Okay, so we had a whole bunch of sparse linear models, and that's what our model was. And all the methods were about 73–74% accurate. Okay, so we sent it in. We're all excited. And I was totally right in that the judges had no idea how to judge this, and we totally bombed in the competition. But luckily, the judges realized afterward that their judging criteria was not really great, and they saw value in what we did. So they actually invented a special prize for us. So they wrote on their website, they said, the team representing Duke University, and there's all of my colleagues, received this sort of special award that they created for us, the FICO Recognition Award, acknowledging their submission for going above and beyond expectations with a fully transparent global model and a user-friendly dashboard, and supposedly we'll get $3,000 someday. I'm just kidding about that. Okay, so anyway, I was so excited about this, and I thought, oh yeah, this is great. Why don't we send this paper into a special issue of a fancy journal? And before I do that, and it was on decision making, so I sent the editor of the special issue an email saying, dear esteemed professor at esteemed university, we don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper. It's a contribution. Its contribution is an analysis of the FICO data, including a machine learning model that is interpretable. It won this challenge. And the response I got back was this. Dear Cynthia, thank you for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for the special issue. It's also related to my own recent work on explainability of neural nets. Is the data set still available? If so, could you share it? Come on, I send the guy a paper saying, you don't need a black box for this data set. And he sends me back an email saying, I don't care about your work, but can you send me the data so I can create a black box and explain it? And that's unfortunately the state of where things are at the moment. Now, I don't know if there's anything I can really do about this, but at the very least, I can try to create, try to make tools available to create interpretable models so that there's at least an alternative to the black boxes. So let me tell you what's going on in my lab. All right, so the first project that we've had going on for many years is optimal decision trees and decision lists. So what we're trying to do is minimize this objective. So this is a combination of misclassification error and sparsity. It has to do with trying to keep the model as accurate as possible, but also try to keep the number of leaves in the tree small. Now, CRUD and C4.5 do not minimize that objective. They do splitting and pruning. So for those algorithms, you would choose the top split, and then you would choose the splits below it, and you would never go back and change the top split if it wasn't right. Whereas for us, the whole thing has to be globally optimized with respect to that function. This is a hard problem. It's NP hard. There's no polynomial time approximation. But we have to solve it because otherwise people will continue to use CART, which is from the 1980s. Okay, so we have computers that are 1 million times faster. We can take advantage of that. The key is a very efficient branch and bound strategy combined with some computer systems techniques to speed the computation up and leverage the way that, the memory is laid out in the computer. Okay, so this model over here is an optimal decision tree on the rearrest data. I love these beautiful sparse decision trees for things like the iris data set. Okay, so this is an optimal sparse decision tree for iris. It's really sparse. Okay, so there are a number of theorems in this project that work together to prune off large portions of the search space. So for instance, there is a theorem that is a lower bound on the node support. And the bound says that for a tree to be optimal, the support of each node must be above 2 times the regularization parameter. So for instance, if the algorithm tries to split on age greater than 70, well, guess what? There's not that many people in the data set who are criminals above the age of 70. For some reason, people above 70 don't like to commit crimes that often. Okay, so in that case, what will happen is that you won't have enough people in that node to lead to a sufficiently optimal solution. So the algorithm will say, I'm no longer splitting on age greater than 70, and in fact, it will not split throughout the entire left side of the tree on that particular feature. Okay, so we have another theorem that is a lower bound on classification accuracy. So not only do you have to have enough support, you have to be accurate enough. Okay, so each leaf of an optimal tree correctly classifies at least a fraction C of the data, where again C is the regularization parameter. So if C is 0.01, that means you've got to classify, each leaf has to classify at least 1% of the data correctly. Okay, so for instance, if you try to do some splits like this, well, maybe there's not too many people with felony above 5, and in particular, there aren't enough people to have this particular node be accurate enough to classify at least C times N points correctly. So in that case, the algorithm would say, no, this is not a good split. I will not be doing that again. And I'm crossing off not only that split, but I will never use that split. I won't continue any of its children. I will eliminate that entire part of the search space. The permutation bound has been another very powerful bound for us. And it says that if 2 trees have the same leaves up to a permutation, their child trees will all be the same up to a permutation. So one of these 2 can be pruned. So for instance, these 2 trees the contents of their leaves are the same, right? It's the same splits, it's just they've been done in a different order. And so these 2 trees are equivalent to each other. Now, if you know this information, you can collapse these 2 trees into a single tree. But in order to do that, we actually had to create data structures that would allow these symmetries to allow us to know whether these symmetries were present. So we created 2 maps. They're called symmetry-aware maps, and they keep track of leaf and tree symmetries so that whenever we create a new tree, we have to go look it up to see whether we've seen those leaves in a different configuration before. In which case, if we have, we can collapse them into a single equivalence class. Okay, and there are several other theorems that I don't have time to discuss that help us lop off big chunks of the search space. We also have a bit vector representation of trees as a collection of leaves. So each tree is represented only by its leaves, which allows us to check easily for things like equivalences. We have a specialized bit vector library to evaluate decision trees very fast. So the combination of us being able to chop off big chunks of the search space at the same time as being able to evaluate the trees very quickly within the search space is what helps us do this optimization, solve this optimization problem quickly. Now, we observe for this algorithm, runtime is approximately linear in the amount of data, so it scales very nicely in the amount of data. However, it's exponential in the first few features, though it tends to be sub-exponential for more features because of all of those theorems that I showed you that help reduce the size of the search space. And this project extends work on corals, which I showed you at the very beginning of the talk. Now, Corals is kind of a well-developed project at this point, and it has Python and R interfaces to our C++ code. And you can just go to the Corals website if you want to and try it out. And it has like an online demo that you can play with. Okay, so these algorithms actually run in reasonable amounts of time for data sets that are the size of our criminal justice problems. All right, so let me talk about interpretable neural networks for computer vision, because I mentioned at the beginning of the talk that you could potentially add some constraints and not lose accuracy. And so we've been trying to figure out how to do this for computer vision, and we wanted to do a form of case-based reasoning, because I like case-based reasoning, and it seems to lend itself naturally to computer vision. And we didn't want to do k-nearest neighbors, though, because nearest neighbors, to me, didn't make any sense for computer vision, because you don't want to compare a whole image to another whole image. What we wanted to do was compare pieces of an image to pieces of other images, okay? So what we've been doing is something that's sort of like k-nearest patches of prototypical neighbors. And the way the algorithm works is it says, this part of the image looks like that prototypical thing from that class I've seen before. And this part of the image looks like that thing I've seen before. And this part of the image looks like that thing I've seen before. And so since it was doing this looks like that, we said, okay, we'll call the network this looks like that. Let's call this looks like that. Okay, so here's how it works. So this is an image on the left, a test image that we're trying to classify as a type of bird. And these are copies of that bird. And so are these. This is also copies of the bird. And what the network is doing, it's saying that this part of the bird over here, well, it's actually this part of the bird, looks like this part of that bird, and that is a prototypical clay-colored sparrow. And this part of the bird over here, this part, looks like that part, this part of that bird. And that's a prototypical clay-colored sparrow. And so on. So this part of this bird looks like this part of that bird. Okay? And so it forces, these constraints, it forces the network to reason about cases. And it's built from a black box model, and it tends to get reasonably similar accuracies to the black box model that we started with. So the architecture, the way it works is that you take your favorite black box model, VGG or whatever you want, take your favorite black box, and then you add an extra layer on the end, which is the prototype layer. And the prototype layer forces you to compare the test image with all of the patches from each of the prototypes that you've learned in training. And then there's a linear model at the end to do the scoring. And so, as I mentioned, you take the black box and you augment it with this extra stuff to force it to be interpretable, but we still found that you weren't losing very much accuracy, if any, by doing this. Okay, so let me show you how the scoring works. So let's say we're trying to classify this thing. Okay, so we ask, okay, why is this bird classified as a red-bellied woodpecker? And so it takes the image, and it says this part of the image looks like that, sorry, this part of the image, this image, looks like that part of this image, which is a prototypical red-bellied woodpecker. And then this number here is the similarity score of that part of our image to the prototype. So it's saying this is how similar I think the head is to the prototype's head. And then there's a class connection weight of that prototype to that class. Okay, so how much does this image over here represent the red-bellied woodpecker class? And so it calculates the similarity score of each of these important patches of the test image to the patch of the prototypes, and then uses the class connection weights to weight those similarity scores, and then add them all up, and that's the total score for the red-bellied woodpecker class. And then if you compare, you do this for all the classes, okay? And then whichever class gets the most points, that's the one that is the chosen class. Okay, so this is the second highest scoring class, which is the red cockaded woodpecker. And this image doesn't look like a red cockaded woodpecker. The only thing that's kind of similar is the pattern on the wing. And so it does the best it can to try to show similarity based on the wing pattern, but it just can't get the number of points for that class as it did for the red-bellied woodpecker class. Okay. And then this project is on optimal sparse linear models with integer coefficients. This project is, again, a very well-developed project. I'm going to show you this by showing you an example of the kind of recent work that we've done. So I work with neurologists, in particular Aaron Struck and Brandon Westover. Aaron is at the University of Wisconsin, and Brandon is at Massachusetts General Hospital, and they both run critical care units at the ICU. Okay, so these guys are working with stroke patients. Now, if you have an aneurysm in your brain and it bursts, you can have a hemorrhage where there's blood in your brain, and then after they do the surgery to repair you, they put you, on monitors, on EEG monitors, to determine whether you're likely to get a seizure. Because if you do, you could be very heavily at risk for brain damage. And so the doctor's job is to really make sure that you do not get these seizures. Now, seizures, they're not like visible seizures that you can see. They're actually seizures in your brain, and in order to see them, you need to be monitored with EEG monitors. Now, EEG it's the only way to detect these seizures. Good way to get the seizures, good way to predict the seizures, to use the EEG data to do the predictions. The problem is that EEG is expensive and it's not well utilized in hospitals. There's a lot of patients who get it, who don't need it, and patients then who need it don't get it. Okay, so we wanted to predict seizures in advance to determine who needs to continue to be on EEG monitoring and who needs to be treated. Okay, so using data from the Critical Care EEG Monitoring Research Consortium, we developed a scoring system. It's a very sparse linear model with integer coefficients. It's the kind of model that a doctor might create by hand before machine learning was invented. And the model looks kind of like this. In fact, it looks exactly like this. This is the whole model. It's called the 2 helps 2B score. And 2 helps 2B is 2H, which is right there, E, L, P, S, and 2 points for the B. And then the total number of points gets added up, and it translates into a risk for stroke within a time period. Now, the algorithm created this model. It chose which of the over 70 features to put into this model, and it created the point scores itself. Okay? So I'm going to show you the optimization problem that we solved to get this model in a minute, but I want to at least tell you a little bit about its usage, which is just as accurate as the black box models. It doesn't force you to trust it. Doctors can decide themselves whether to trust it. It has led to a 63.6% reduction in the duration of EEG monitoring per patient in 2018, according to Aaron and Brandon in these 2 hospitals, and that allowed them to monitor 2.8 times more patients, which, according to them, this is a big deal because it actually helps reduce brain damage and saves lives. Okay, and then they measured that it saved over $6 million at these 2 major hospitals last year, and it's being used now in several other hospitals. And this savings is just due to taking people off EEG monitoring when they don't need it. Okay, so let me get back to the modeling here. So what is this model? This is a sparse linear model with integer coefficients. And you just sort of count how many things the patient had. You don't need a calculator. You can just read the EEG and go. However, creating a model of this form is kind of difficult because to create it, we had to solve a mixed integer nonlinear program, which is very difficult, and we ended up developing a new cutting plane algorithm in order to do it. So let me tell you what the optimization problem is. It's actually aiming to solve a combination of minimizing logistic loss to try to keep these probabilities accurate and calibrated, and then trying to keep the size of the model small. So this is just the number of terms in the model. And then this restriction here, this constraint, lambda is in this set L, means that the coefficients had to be between -10 and 10. And as you saw, the resulting coefficients in 2 helps 2b are just 1 and 2. Okay, so this is, again, a mixed integer nonlinear program. It's not easy to solve, but we developed a cutting plane method that combines branch and bound, elements of branch and bound within the cutting plane technique in order to solve it, and it works. You know, the code's publicly available, and you can download it and use it for whatever problems you want. Okay, and then the last problem I wanted to talk about is the FLAME project, which is a fast, large-scale learning to match for causal inference. Okay, so FLAME, our goal was to do matching for causal inference. So if you have treatment patients and control patients, and you generally want to know you want to know what the effect of the treatment was. And so if you try to match people to like their identical twin in the control group, then you can look at these kind of groups of identical patients and use that information to figure out the treatment effect, or estimate the treatment effect. So our goal was to match treatment units to control units as closely as possible. And we were doing this under the standard assumptions in causal inference, like the stable treatment value assumptions. So the standard assumptions in causal inference, in the potential outcomes framework. Okay, so we started with working with categorical data, and we said, okay, for each treatment unit, let's try to find a control unit that matches on as many covariates as possible. But see, that doesn't make sense exactly, because some covariates are more important than others, right? It could be that there are features there that are not very useful, so you don't care about matching on those very much. You really want to match on the very important features like, history of stroke or age or something like that. So we decided to weight the covariates, and then we decided to use machine learning to figure out what the weighting of the covariates should be. So we actually held up part of the data and used that to figure out which covariates we really needed to match on. Okay, so we ended up solving the following optimization problem. So for each treatment unit, try to find a set of covariates, this is a set of covariates, such that it maximizes a weighted sum of the covariates that are being used. And again, the weights come from the machine learning on a training set. And we wanted to choose as many weighted features as possible so that there is a control unit that matches on these weighted covariates. Okay, and the algorithm for doing this is really cool. It uses lots and lots of SQL group by queries. We have a database expert on our team, so we use lots and lots of SQL group by queries that are very efficient. And then we use a property that's similar to the downward closure property in the a priori algorithm to help us create the matches for all the data points very fast. Okay, so in summary, I've defined a condition under which a simple yet accurate model is likely to exist, which is that the Rashomon set is large, which is that there's a large number of good models. And I showed a simple check for large Rashomon sets, which is that lots of machine learning methods tend to perform this very similarly. I also introduced Rashomon curves, which we found in every single data set that we considered, and they seem to help us understand why different problems seem to behave differently in machine learning. And I discussed some of the work we're doing in the lab on computationally efficient solutions to some of these hard problems, including optimal decision trees, interpretable neural networks, optimal scoring systems, and learning to match for causal inference. And these are my collaborators. Thank you.
Please come to the microphone to ask any questions. And while we wait for somebody, I have a question for you, Cynthia.
Sure.
A fantastic talk. Really enjoyed it. And one of the key components in your talk is to determine, one of the conditions is run many algorithms and see if they are doing equally well. How do you know that you have seen many algorithms, in the sense that is there a way to figure out that I have tried enough algorithms to see whether I'm satisfying that condition?
Yeah. So it's kind of a loose guideline, right? There's no like concrete guideline, but I usually try the sort of standard array of algorithms. So I try, if you can get something like with SVM with radial basis function kernels, so it's a very smooth function, right? And then you compare that to something like decision trees, where it's a very, very not smooth function, then you know that you have very different types of functions that are in that same Rashomon set. So I usually just go by sort of my own knowledge of what the function classes are that I'm working with. But we haven't yet developed a hard and fast rule for that. I mean, we're just sort of proposing what we think is a reasonable explanation for what might be going on. So I think it's a little, I mean, we only posted the paper like 3 days ago, so it's a little early for us to have concrete guidelines on that.
Okay, yeah, thank you. Absolutely loved your talk. And one question, so you motivated the Rashomon course, and you looked at training set and test set, which is good, but I think in practice, when you have a model that runs over years or months...
Wait, I couldn't hear what you said. Could you say the last thing you said?
So if you have a model that runs in practice over years in some application, one thing that usually happens is that you have some concept shift there. So in the end, the distribution of the data changes with time. Oh. And one thing why I like simple models is they seem to be more robust with respect to that. And have you looked into that, and do you have some idea of how the Rashomon curve would look in this case?
Okay, so we have not. We've only been looking at standard supervised settings without distributional drift. But I can see exactly what you're saying, and it totally makes sense. We just have not looked at it yet. Yeah.
Okay, thank you very much for a very insightful and mind-bending talk with a really refreshing perspective. I have a couple of questions about your Rashomon theory. The first one's kind of a stupid question, but how did you come up with the Rashomon set and these notions? Is it a pre-existing notion that has found use in other contexts, or is it totally your invention? That's my first question. The second question is, if you have a big, auto machine learning kind of meta-learning algorithm, and if you optimize the sum of empirical loss plus complexity, were they likely to find the elbow point in your, if you include all the classes of interest? So those are my two questions.
Okay, so those are really good questions. Okay, so the first one was, how did we come up with it? And the answer is that it seems obvious in retrospect, because my lab has been working on interpretable models for years, right? Almost my whole career I've been working on interpretability. And so we always do experiments to figure out whether we're losing any accuracy. And we just didn't seem to be losing any accuracy from most of these problems that we ended up working on, these problems in healthcare and energy and criminal justice. And, it just seemed to be that, what's going on? There's so many, all these models from SVM, from random forest, from boosting, they're all performing the same, along with our very simple itty-bitty models. So what could be causing this? And so it's kind of, it's something that for me seems obvious, but it didn't seem obvious. The Rashomon curves are definitely not obvious. Those are weird. So I think, we just came up with it by just experimenting and playing with data. And then the second question was, sorry, remind me what the second question was?
If you had a meta-learning algorithm, like an auto-ML type, that, uses all the classes of interest, and if you minimize the loss plus complexity, would it be likely to find the elbow point?
Yeah, so I think that elbow point is probably something that would be found by any model selection criteria. So I think it should be found by things like AIC, BIC, Bayesian Occam's razor, you name it, model selection criteria. I am hoping that it ends up at the elbow, but we haven't tested that yet.
Right. Okay, thank you.
Mm-hmm.
So this was really interesting, but I just had one quick question, which is, how exactly are we defining complexity? Because I feel like it's something that we have an intuitive understanding of in cases like linear model versus neural network with 500 layers. But what about situations where you may have many features that are important, and you're comparing like a linear model with no regularization into like a random forest that's more complex but automatically has like fail-safes to try to prevent overfitting.
Okay, so complexity has many definitions. I listed a whole bunch of them in my talk, so Rademacher complexity and VC dimension and so on. So, I mean, when I'm talking about a hierarchy of these spaces, I'm actually increasing VC dimension, Rademacher complexity, all that stuff. You could also think about increasing the margin, so increasing the regularization parameter. All of that stuff will translate into increased complexity. It's not clear exactly how that translates to exactly where the elbow is on that curve, but I'm using any of those definitions. Yeah.
Okay, so my question is actually related. I was wondering if you have any invariant way of computing this volume of this Rashomon set or the full space of functions, because I'm just concerned that the results might depend on how you measure this.
Yes, we have a large discussion about this in the paper because we debated about this over and over again. So luckily you never have to measure the size of these functions in practice because otherwise you would run into this problem. So we proposed 3 different ways of measuring it. The first way is to actually measure it based in function space using something like L2 distance, like LP distance or something like that. So just purely distance between functions. The second way we propose to measure it is to use distance in parameter space. For something like linear models, we can measure volumes in parameter space pretty easily. The third way we proposed measuring it is using what's called the pattern Rashomon ratio that I didn't discuss, which is just using, which is looking at, it sort of lumps all of the functions together that predict the data the same way. So for instance, if you have 2 models that when you change them, none of the points get classified differently. All those models get lumped into one class. And then we look at the fraction of patterns, essentially, that are good as the Rashomon ratio. So, yeah. But you're right, it does matter, because if you measure it, like if you measure the denominator to be too big, that's what we think caused the issues with our experiments that I was telling you about, where we measured a small Rashomon ratio, but yet everything generalized and everything performed the same. Yeah.
Thank you.
Thank you.
My question is perhaps a little bit more philosophical. So when you showed the use case, I think with stroke, where you had the model that developed that thing that was very interpretable to doctors, and doctors can trust it, right, and they can verify it. As you mentioned, you could create a simple model that's about the same performance. Well, if you can create a black box that's, say, 1% better performance, at which point is there a trade-off between saving 1 out of 100 patients, for example? Meaning, when is accuracy and interpretability, how do you value them when there's that kind of trade-off, even when it's close?
Yeah, that's a good question. Luckily, we've never had to sacrifice accuracy to gain interpretability in my applications. So I never actually had to answer that in practice. That's why we started working in computer vision, because we thought, oh, we'll definitely have to sacrifice interpretability in computer vision. But then after doing this case-based reasoning stuff, I no longer believe we have to sacrifice accuracy to gain interpretability. So, I mean, your question in theory is an important, interesting one, but in practice, I haven't actually run into the case where I've had to sacrifice accuracy.
Thank you.
Mm-hmm.
Thank you for the talk. So my question is about methodology and data set itself. You mentioned that the methodology is relatively independent of the data that you're using. I'm just curious that are there any type of data or like topics that better fit in this simple, methodology? For example, like neural network is really good at like vision and language processing. So do you have any insights about for these tasks that are traditionally human do much better than machine? Can we find like a simpler method?
I think you're asking about the data representation, right? So neural networks are really good at creating data representations. So that's why you really need them for computer vision, because there's no other technique that I know of that can achieve that level of accuracy for computer vision. Because they're creating a specialized data representation. That's fine. It's just and they also, computer vision also has very different types of interpretability. Like you'd never want to use a sparse decision tree on pixel space. It wouldn't make any sense. It wouldn't be interpretable. So, I mean, this is a very domain-dependent question. And like I said, I think the Rashomon curves are just different for different domains. And so when you're talking about something like computer vision, you can get very, very accurate models, but you have to increase complexity a tremendous amount in order to do it, because you have to create that data representation. Whereas for these medical problems that I work on, they already come with a good data representation. So, you're fine with a sparse linear model with integer coefficients.
Okay, thanks.
Thanks.
Thank you for the talk. When does something like a rule list become uninterpretable? So we used to have rule-based system in the past, and they kind of tend to collapse under their own complexity. So when does also something like your FICO score system that essentially has 2 layers that are interpretable, like if it had 5 layers, would it still call it an interpretable model? I mean, at some point, we can have like nested rules of rules and whatnot, and sure, it's interpretable up to a point, right?
Well, that's why we do everything with that's why we do everything with sparsity constraints. That's why our decision trees are optimal sparse decision trees. That's why our optimal sparse decision lists, because we want everything to be sparse, and that's why our linear models are sparse.
Okay.
And that's why,
How do you quantify that? Like, 3 layers, three a depth of 4, it's, humanly interpretable?
Well, humans can, there's this very famous paper from, I think, 1950, that humans can only comprehend 7 plus or minus 2 cognitive entities at once. It really depends on the domain. You can't even define interpretability separate from the domain. Just like you can't define a performance measure outside of a domain. You really need the domain knowledge to define what is interpretable in this domain.
We observe that for deep neural networks, people often need to train very large deep neural networks and then compress the network to get a simpler model. It's because the smaller model is very hard to train. Bigger model is easier to train, but compressing them after is possible. So I just wonder, with your theory, can your theory provide any new insight to this kind of approach? Because I always found if we can train a simple model in the beginning, it will be supposed to be a better approach than first to train a larger model than compress it, right?
Okay, so let me just make sure I understand the question. So you've trained a very large, accurate model, and then you're trying to, from there, construct try to simplify the model without losing accuracy.
Yes.
Yeah, that's what I do too. That's what first we start by, trying to get the most accurate model we possibly can on the data set. That gives a baseline. And then if we can get up to that baseline with an interpretable model, we are happy, because now we've solved the constraint problem to get as interpretable as the more accurate one. And so, I think that's a great way to do it. I'm not sure if the Rashomon set theory will help at all, except by saying that if the Rashomon set of the problem is large, then you can find it a more interpretable model. But I'm not sure it'll help. Help you actually find it.
Be able to tell us there indeed exists a simpler model, and so compressing it is possible or promising.
Yeah. We sort of designed this theory to sort of convince people to try to do this, to try to do this, and not just give up once you've sort of gotten the accurate model and try to explain it afterward, which doesn't seem to always work very well. So thank you. Yeah.
So thanks for helping us focus back on the carbon footprint of deep learning. So have you considered, so it's very clear that simpler models give great accurate results, and there is a good debate that we are having about the ability of complex models versus simpler models in production. But do things like the Rashomon curve or the loss function, process that you have gone through, does it also vary with the size of features? Because as the number of size of features increases, there is increasing popularity for using methods like deep learning for auto-encoding and arriving at a smaller subset of features that are latent features. And that's where I feel that there still might be a disconnect. So any thoughts on that?
Well, I mean, the question was whether we can solve just a straight model without the constraints versus solving the problem with the constraints. And whether or not these things are equal depends on those constraints. So if you make the constraints too intense, forget it. It's not going to work, right? So if you're trying to solve some, handwriting recognition problem with a sparse decision tree, it's not going to work because your constraints are too heavy. But if you do, if you're willing to change your definition of interpretability so the constraints won't harm accuracy, then you can potentially not have a problem. So, for example, in the computer vision project that I showed you, forcing the algorithm to do this kind of k-nearest neighbors thing does not seem to harm accuracy. So I claim that if you want to introduce interpretability into your neural network, whatever form it takes, you can probably do it. I just don't know exactly what your problem is and what your constraints ought to be.
We'll take this last question.
Yes, okay. Just one quick question about finding the practical way of finding the large Rashomon set. Like you said that when multiple methods are giving you the same accuracy, that's a good indication of an existence of a large Rashomon set. So could it be that there is some problem with the data that's saturating these models? For example, the compass accuracy, I see that it's saturated at 74%, 75%, right? So is there any way to, using the Rashomon curve, is there any way to clean up the data or identifying issues with some features in the data that is not helping learning anything? Is that a problem?
Yeah, that's a good question. I think that there's just a level of noise in these data that there's no way to really get around. So for instance, with criminal recidivism, you're trying to predict whether someone's going to be arrested within 2 years. Now, 2 years is a very short period of time. So the chance, maybe that person is at high likelihood for being arrested, but maybe they get arrested after that 2-year period ends. Maybe they get arrested in the 3rd year. And the shorter you make this time period, the harder it is to predict because it's just a noisy problem. So I don't think any amount of feature cleaning would actually solve this, although I do think that that the data, we're working with data that's straight from the sheriff's department, from the county clerk's office. Even that data is kind of noisy. So you don't exactly know what the person's criminal history is. You don't have any data about their, you don't exactly know what the extent of their drug abuse situation is. And if you knew that extra information, you could probably predict better. But still, the level of noise, I don't think there's any way around it. Yeah.
Let's take the opportunity to thank the speaker for a fantastic talk again.